At the end of this video, you should be able to summarize the observed properties of cathode rays that led to the discovery of the electron and define atom. Chapter 3, Section 2, the structure of the atom. Although John Dalton thought atoms were indivisible, investigators in the late 1800s proved otherwise. As scientific advances allowed a deeper exploration of matter, it became clear that atoms are actually composed of several basic types of smaller particles, and that the number and arrangement of these particles within an atom determine that atom's chemical properties. Today, we define an atom as the smallest particle of an element that retains the chemical properties of that element. All atoms consist of two regions. The nucleus is a very small region located near the center of an atom. In every atom, the nucleus contains at least one positively charged particle called a proton, and usually one or more neutral particles called neutrons. Surrounding the nucleus is a region occupied by negatively charged particles called electrons. This region is very large compared with the size of the nucleus. Protons, neutrons, and electrons are often referred to as subatomic particles. The sizes of atoms. It is convenient to think of the region occupied by the electrons as an electron cloud, a cloud of negative charge. The radius of an atom is the distance from the center of the nucleus to the outer portion of this electron cloud. Because atomic radii are so small, they are expressed using a unit that is more convenient for the sizes of atoms. This unit is the picometer. The abbreviation for the picometer is PM. 1 picometer is equal to 10 to the negative 12th meters, or 10 to the negative 10th centimeters. To get an idea of how small a picometer is, consider that 1 centimeter is the same fractional part of 10 to the third kilometers, which is about 600 miles, as 100 picometers is to 1 centimeter. Atomic radii range from about 40 to 270 picometers. By contrast, the nuclei of atoms have much smaller radii, about 0.001 picometers. Nuclei also have incredibly high densities, about 2 times 10 to the 8th metric tons per cubic centimeter. Discovery of the electron. The first discovery of a subatomic particle resulted from the investigations into the relationship between electricity and matter. In the late 1800s, many experiments were performed in which electric current was passed through various gases at low pressures. Gases at atmospheric pressure don't conduct electricity very well. These experiments were carried out in glass tubes like the one shown in Figure 3-4 on page 70 of your text or on the screen now. Such tubes are now known as cathode ray tubes. Cathode rays and electrons. Investigators noticed that when current was passed through a cathode ray tube, the surface of the tube directly opposite the cathode glowed. They hypothesized that the glow was caused by a stream of particles, which they called a cathode ray. The ray traveled from the cathode to the anode when current was passed through the tube. Experiments devised to test this hypothesis revealed the following observations. 1. An object placed between the cathode and the opposite end of the tube cast a shadow on the glass. 2. A paddle wheel placed on rails between the electrodes rolled along the rails from the cathode toward the anode, as is shown in Figure 3-5 on page 71 of your text or on the screen now. These facts supported the existence of a cathode ray. Furthermore, the paddle wheel experiment showed that a cathode ray has sufficient mass to set the wheel in motion. Additional experiments provided more information. 3. Cathode rays were deflected by a magnetic field in the same manner as a wire carrying electric current, which was known to have a negative charge. 4. The rays were deflected away from a negatively charged object. These observations led to the hypothesis that the particles that compose cathode rays are negatively charged. This hypothesis was strongly supported by a series of experiments carried out in 1897 by the English physicist John Joseph Thomson. In one investigation, he was able to measure the ratio of the charge of the cathode ray particles to their mass. He found that this ratio was always the same, regardless of the metal used to make the cathode or the nature of the gas inside the cathode ray tube. Thomson concluded that all cathode rays are composed of identical negatively charged particles, which were later named electrons.
When the cathode and anode of a cathode ray tube are connected to a voltage source, electric current flows through the tube and can be seen as a cathode ray. The cathode ray is made up of electrons. When a positive electric field is placed next to the tube, the path of the electrons moves toward the field. Using the strength of the electric field and the amount of deflection, J.J. Thomson was able to calculate the ratio of the charge of electrons to the mass of electrons. Imagine a baseball player throwing a ball. Like the cathode ray, with no outside influences, the ball goes straight when the baseball player throws it. A strong wind, however, could blow the ball and make it go off course. An outside positive field attracts the electrons in the cathode tube and makes them go off course. If the baseball player threw a lightweight plastic ball instead of a regular baseball, the wind's effect would be even more evident. The mass of the ball is one of the factors that determines the path the ball will take. Similarly, if the wind were stronger and the baseball player used the original ball, the wind's effect would be more evident. The strength of the outside force is one of the factors that determines the path the ball will take. By observing the path of electrons in the cathode tube, Thomson was able to calculate the ratio of charge to mass of an electron.
Charge and mass of the electron. Thomson's experiment revealed that the electron has a very large charge for its tiny mass. In 1909, experiments conducted by the American physicist Robert A. Millikan showed that the mass of the electron is in fact about 1/2000th the mass of the simplest type of hydrogen atom, which is the smallest atom known. More accurate experiments conducted since then indicate that the electron has a mass of about 9.109 times 10 to the negative 31st kilograms, or 1,837th the mass of the simplest type of hydrogen atom. Millikan's experiments also confirmed that the electron carries a negative electric charge, and because cathode rays have identical properties regardless of the element used to produce them, it was concluded that the electrons are present in atoms of all elements. Thus, cathode ray experiments provided evidence that atoms are divisible and that one of the atom's basic constituents is the negatively charged electron. Based on what was learned about electrons, two other inferences were made about atomic structure. 1. Because atoms are electrically neutral, they must contain a positive charge to balance out the negative electrons. 2. Because electrons have so much less mass than atoms, atoms must contain other particles that account for most of their mass.
In Millikan's oil drop experiment, he squirted negatively charged microscopic droplets of oil into a chamber and observed them with a microscope. Voltage applied to metallic plates within the chamber allowed him to create an electric field, which had an effect on the droplets. By adjusting the electric field's strength and direction so that it pushed the droplets against gravity, he could suspend the droplets. By knowing a droplet's mass and the strength of the electric field needed to suspend it, he calculated its charge. Testing several droplets in this way, he found each droplet's charge to be a whole number multiple of 1.602 times 10 to the negative 19 coulombs. This is the charge of an electron.
At this point, you should be able to summarize the observed properties of cathode rays that led to the discovery of the electron and define atom.